Good day everyone, welcome back to Engineering Online. On this video we are going to talk about transformers. We know that transformers are electrical devices which are used to step down voltage or step up voltage without affecting the apparent power. Now before we start working on this transformer, I want us to understand the principal operation of a transformer. And to understand the principle of operation of a transformer is to make use of the simple circuit diagram of a transformer. Now the simple circuit of transformer consists of the primary winding and the secondary winding. It's like this. So now, how does a transformer operate? Transformer operate using the principle of electromagnetic induction, which are Faraday's laws, which states that in a current carrying conductor, a magnetic flux is going to be induced around a conductor. And the second law states that when a magnetic flux cuts through a conductor, it's going to induce an EMF. So these are the two Faraday's law that are going to make use of understanding the operation of a transformer. So now to explain it, we are going to explain it like this. A transformer operates using the principle of electromagnetic induction, and there is no physical connection between the two windings. When we apply voltage V1 in the primary, current I1 will flow in the primary. This current will induce a magnetic flux, or it will produce a magnetic flux which will cut through the secondary winding N2. When it cuts through the secondary winding, it will induce an EMF V2 in the secondary, which will cause current I2 to flow in the secondary. That is how easy this thing is. You can explain it like this. Let me repeat. When you supply the voltage V1 in the primary, a current I1 will flow in the primary, which will produce magnetic flux, which will cut through the secondary winding. When it cuts through the secondary winding, it will induce an EMF, which will cause V2 to be induced in the secondary, which will produce I2 in the secondary. Let me repeat now. When we apply a voltage V1 in the primary, current I1 will flow in the primary, which will produce a magnetic flux in the primary. This magnetic flux produced by the primary winding will cut through the secondary winding and then inducing an EMF V2 in the secondary, which will cause I2 to flow in the secondary winding. That's how a transformer operates. Now we know that in any given conductor and a coil, to be specific, we are going to have inductance and resistance. So because of that, we are going to have an inductance and a resistance in the primary, and a resistance in the secondary, and an inductance in the secondary. R2, X2, R1, X1. So we apply voltage V1 and then we receive voltage V2. So now to calculate voltage V2 accurately, the terminal voltage in the secondary, we have to consider the impedance as well. So when we are calculating step by step, we are going to calculate like this. V1, when current flows here, we are going to have VZ1 here. And then we're going to have E2 here, and we have E1, and then we're going to have E2 here, and VZ2, because it is Z1 and this is Z2. So now when current flows here, we are going to have a voltage drop. So to get the EMF induced in the primary, it's going to be V1 minus VZ1, and we get E1. Then we use the transformer ratio, which is N1 over N2, to get E2. E1 over E2. After we got E2 minus VZ2, we get V terminal, which is V2. So when our engineers sat down and look at this diagram, they saw that this diagram now it's becoming complicated. And engineers don't like complicated things. They want to make things easy. Like we know that technology is the ability to make life easy. So they decided to refer the secondary winding to the primary in order to make the calculations more accurate and easy. So when we refer to the secondary, or when we take the secondary winding and we refer it to the primary, it's going to look like this. We're going to have primary voltage, primary resistance, secondary resistance, primary inductance, secondary inductance, and then we're gonna have our transformers like this. Then we're gonna have R1 and R2 prime, and then we're gonna have X1 and X2 prime. So now it's easy. We have V1, we have E1, we have E2, and we have V2. So now we can see that E2 is equal to V2. The calculations are a little bit more easier. So to calculate, to transfer this secondary impedance to the primary impedance, we use this formula. To get R2 prime, we are going to say R2 N1 over N2 squared. Or we can use, this is just the transformer ratio. So you can even say R2 is equal to V1 over V2 squared. You can also say it R2 times I2 over I1 squared. And then similarly for X2 prime, we're going to say X2 N1 over N2 squared. And then now we have to calculate the total impedance referred to the primary. We usually say it's an equivalent impedance. So it's going to be RE1, which is going to be R1 plus R2 prime. So we can say this is R1 plus R2 N1 over N2 squared. And then XE1 is going to be X1 plus X2 prime, which is X1 plus X2 N1 over N2 squared. Now when we are referring to the secondary, we are going to have the primary like this, and then we are going to take the primary resistance and refer it to the secondary. We take the primary impedance and refer it to the secondary. So now we are going to say when we are referring the primary to the secondary. When we are referring to the secondary, we have to calculate RE2, which is going to be R2 R1 prime X2 X1 prime, which is going to be R2 plus R1 prime. So now R1 prime is calculated using the formula R2 plus R1 N2 over N1 squared. Please notice this inverse. Similarly, it's going to be V2 over V1, I1 over I2. And then we're going to calculate X2, which is going to be X2 plus X1 prime, which is X2 plus X1 N2 over N1 squared. Okay, now we are going to consider the example that is given on 3.1. So it states that a 200 kVA single-phase transformer has 600 turns on the primary winding and 120 turns on the secondary winding. The primary and the secondary resistance are 0.35 and 0.02. the corresponding leakage reactance are 1.4 ohms and 0.045 respectively. The supply voltage is 3.3 kilovolts. And we are asked to calculate the equivalent resistance and the reactance referred to the primary, the impedance referred to the secondary. Roman figure 1. So to get the resistance is going to be RE1, which is the equivalent. It's going to say it's R1 plus R2 N1 over N2 squared. Don't forget this squared here because your answer is going to be wrong. And then this is equal to 0.35 plus 0.02. The primary winding is 600 over the secondary winding is 120 squared. So this is going to give us 0.35 plus 0.02, 600 over 120 squared. This gives us 0.85 ohms. And then to calculate the equivalent resistance, impedance, and now to calculate the equivalent reactance referred to the primary, it's going to be X1 plus X2 N1 over N2. This is going to be 0, sorry, this is going to be 1.4 plus 0.045 600 over 120 squared. 1.4 ne? .525 ohms. That means the equivalent impedance referred to the primary is going to be 0.85 plus J 2.525 ohms. If you don't understand the J notation, you can check the video here, which speaks about complex numbers. I explain complex numbers in detail, so you can just check the video so you can learn complex numbers, and then you can come back here. And then we can also change this to rectangular. Which gives us 2.664 at an angle of 71,395 ohms. So okay, let's do number Roman figure 2, which we are going to refer to the secondary. So when we are referring to the secondary, we have to calculate RE2, which is going to be R2 plus R1 N2 over N1 squared. Please note this. So it's going to be, what's R2? 0.02 plus 0.35 120 over 600 squared. This gives us 0.034 ohms. And then we're going to calculate Xe2, which is going to be x2 plus x1 n2 over n1 squared. This is equal to x2, it's 0.045 plus 1.4, 120 over 600 squared. 45 plus 1.4, 120 over 600 squared. This gives me 0.101 ohms. Therefore, the equivalent impedance referred to the secondary, it's equal to 0.034 plus J 0.101 ohms.